right?
All right. So we are continuing with this discussion, and we know a little bit already. We have talked about places where we have maxes and mins, and we know we can find our absolute maxes and mins from our critical points.
You got a new one?
I got a new one because this one wants to stay charged all day long. I have to like charge it at lunch so it'll last me. I got a new one today, but I haven't plugged it in or anything. So we already know how to find absolute max and min. What we're really going to start focusing on now is local maxes and mins. So we know a little bit. We know that anywhere the derivative is 0, what was true about our original graph?
It's a point of
Slope is,
max.
yes.
Okay, so our maxes and mins, those would all have a derivative equal to 0, right? We call those our critical points. What we haven't really talked about, but we actually do know, is all of these, what's true about those tangent lines? What do they have in common?
Increasing.
They're increasing. They would all have a positive slope, right? Because the graph was decreasing. Between B and C, the graph is decreasing, and what would be true about those tangent lines? They would have a negative slope. So now we know that if the derivative is positive, the original graph was increasing. And if the derivative is negative, the original graph is decreasing. So we can also not just tell absolute maxes and mins, we can tell increasing and decreasing. And we could even extend that a little bit to our maxes and mins. So first, we'll fill in the box here. So if the derivative is greater than 0, the function is increasing. And if the derivative is less than 0, then f is decreasing. So those little boxes out to the side for you to fill in.
I just think it's easier to read like when it's like this than when it's like that. Like I don't understand those sometimes.
Yeah. I don't want to just never show you those in case you have to, take more math classes where they just say go read chapter 1 and we'll have a test on Wednesday. I want you to start getting used to
I don't know if I
seeing
can do
it.
that math class.
Seems
Seems
like-
like scary. We call him Mr. Apple every day.
Okay, so let's figure out whether this function is increasing or decreasing. So what would I have to do first?
Prime of x. Oh, I get it now. I understand it.
So this derivative would be 2x minus 4. Okay, we know that if we're going to be increasing or decreasing, it changes at these points where the derivative is 0, right? So let's go ahead and find our critical points from here. So if I set this equal to 0, so that's my critical point. So what I'm going to do, we could draw a graph of this and that wouldn't be too hard, but some of our functions it will. We're going to go back to this idea of a sine line. Do you remember doing sine lines
Oh.
way back when? So we know 2 is when the derivative is 0. We just need to know when it's positive or negative. So we pick test points. So a number smaller than 2, 1, 0, yep, a number bigger than 2. And we are plugging those into the derivative because I'm trying to decide if the derivative is positive or negative. I don't care what number I get when I plug them in, just if it's positive or negative. And you notice how the only point I actually plotted on my number line was the 2. These I'm just writing above, so I know those are the ones I'm testing, but I just picked those numbers myself. So if I put in a 0, do we get a positive or a negative answer?
Negative.
Negative. So that means we will get negatives for everything smaller than 2. If I put in a 3, I get a
Positive.
positive. So every number bigger than 3 is going to give me positives. So where is this graph increasing?
Well,
Everywhere.
Well, infinity. Oh,
We'll just write interval notation from 2 to infinity. It is decreasing from
Negative infinity to 0. Or yes to 2. I was looking at the 0 one.
Oh, so we do it from, we don't do like the whole thing, we just do it from the.
So that critical point is where it can change, from increasing and decreasing. So those are the breaking points of these intervals.
Are the intervals going to change if it's like not a vertical quadratic function? Like if it's like a,
Yes, you could have, I mean, you'll still have critical points to look at, but it is also possible that you could, when you're testing your critical points, you might get 2 positives in a row or 2 negatives in a row. So don't just get the first one and assume they're always going to alternate. They won't.
So if it's, wait, so it has to be a max, but if it's 2 positives, then how does that work?
So remember, critical points are where you might have a max or a min. You're not guaranteed to have one there. For instance, remember x cubed. X equals 0 is a critical point of x cubed. If you think about that function, is this a max or a min? No. So critical points might be a max or a min, but they do not have to be.
So we don't know if the maxes and min, like absolute maxes and absolute mins we found are actually.
Those are actual. But remember, the key to those is they were on a closed interval. So it's just between these numbers. So what we're looking at now is not really a set interval. We're looking everywhere from negative infinity to positive infinity. Where do we have high and low points? All right, let's do another one. All right, so we do our derivative. We get and what do we need to do with that?
Find zeros.
Find when it's equal to 0. So what would we do first?
We could have
12x.
one
Mm-hmm.
I'm confused on how this works.
Okay. And then we could factor this into,
Minus 2 plus 1.
okay, so my x's, these are my critical points.
0, 2.
Mm-hmm. Okay, so we have 3 of them. So on our sign line, it gets very confusing, like trying to write your interval if you plot your test points on here. So that's why I only put tick marks for the 3 critical points. And we have to put them in order. So -1, 0, and 2. And I just write my test points above it. So what's something smaller than -1?
-2.
In between -1 and 0.
0.5. Negative 0.5.
Between 0 and 2.
1.
And bigger than 2.
3.
And I'm plugging those into my derivative. Now you can do it wherever. You could do it up here, but I'm going to prefer to do it right here. So I think it's a little easier if we're just trying to decide positives or negatives. So if I'm looking at my factored form, 12 times -2 is negative. -2 minus 2 is negative. -2 plus 1 is negative. If you have 3 answers, your answer is, or sorry, 3 negatives, your answer is
Negative.
Oh my gosh. I don't know why
Positive.
I thought you already had a positive up there and I just
Oh.
got.
So if I put in -0.5, 12 times -0.5 is a negative. -0.5 minus 2 is negative. -0.5 plus 1 is positive. So that section is
Positive.
positive.
I knew it. I'm predicting.
If I put in a 1, 12 times 1 is positive. 1 minus 2 is negative. 1 plus 1 is positive. So this section is,
Negative.
and if I put in 3, 12 times 3 is positive. 3 minus 2 is positive. 3 plus 1 is positive. So this section is,
Positive.
Wait, how do we, what?
I'm putting them in right here in my factored form.
Oh.
Because I don't have a
that's-
calculator, I don't really want to have to do -2 to the third, and you know,
That's-
so it's a
that's
lot
way
easier here
Yeah.
in that factored
I
form.
was wondering how you were getting those so fast.
So this is increasing wherever my derivative is positive. Where is it positive?
Between -1 and 0. And then 2 to infinity.
And it is decreasing where it is negative. Where is that?
Negative infinity to -1 and 0 to 2. Is it not no brackets?
Right. Technically, it won't matter, but at a point, you're usually not considered to be increasing or decreasing your.
Cause, oh, 'cause it's gonna be, horizontal.
Yeah.
Gotcha.
Can the points just, like, does this tell us the shape of the graph? Or like, could it just keep going up and down and up and down and up and down, we just don't know it?
We have found, because we have infinity, so we do know
You're just gonna.
that this is going to start off decreasing until we get to -1. Between -1 and 0, it's increasing. Between 0 and 2, it's falling. Between 2 to infinity, it's increasing. So we are learning more about the shape. You could draw me a rough graph,
That's a sine graph, or it's cosine graph.
Yeah.
Since it's higher.
assuming my points are accurate. I was just showing the direction, but yes, we are getting to the point where we know more about our graph. And this, Carson already kind of touched on, but it could also tell us maxes and mins for our local maxes and mins. Because if we look, if I'm decreasing and I switch to increasing, what did I just create? A minimum. If I'm increasing and switch to decreasing, we have a maximum. So, this is the first derivative test. If f changes from a positive to a negative at point C, then f has a local max. So if the derivative was increasing and switched to decreasing, you get a max. If it goes from negative to positive, so you're decreasing to increasing, that's a local min. If your sign does not change, so if it's positive to positive or negative to negative, there is no max or min at that point.
I don't know if they're not absolute.
You would have to have endpoints to guarantee absolute. Or we would have to know, like once we get the graph, if both ends are going down forever, then we'll end up finding the actual order pairs for these maxes and mins as we go through here.
That's a lot to chew on.
Alright, so now let's apply that. I want the local maxes and mins for this function that we just had. Okay, so this was the one we just came up with, right? So look back at your previous slide, example 2. And we already kind of said it was increasing, we have the increasing and decreasing. Okay, so local max and local min. We can have multiple of these. A max means it was increasing to decreasing. At what x values did those occur? Increasing to decreasing.
Zero, -1 to 0, or -1 to 2, question mark?
No, it's just 0.
So our test, here's our sign line that we had on the previous slide. Okay, and we said this was negative, positive, negative, positive. So this was decreasing to increasing. So -1 is a min. Okay. At 0, it's increasing to decreasing. So 0 is a max. At 2, decreasing to increasing. So 2 is also a min.
Oh, we're gonna find it.
And we can give the actual points because if I'm going to graph these later on, we need order pairs. So you can write them in function notation like f of 0 equals whatever, or we can write them like this. If we're getting a point, that's the point on the graph itself, so we need to be plugging them into the equation, not the derivative. What will I get out if I put these back into the derivative?
0.
0. So if I put these into my equation, if I put in 0, we get
7. Oh wait, why am I writing on the wrong one? My bad.
if we put in a -1, so that would be 3 plus 4 minus 12 plus 5.
-7. Oh, wait, what the heck? I can't math, it's fine.
If we put in a 2, so 4, 5, -27.
I agree, I have blind faith.
I believe.
So that's where we have our local maxes and mins. Okay, do you guys think you can try one?
Oh, I sure can.
I know
So-
I can.
Find the critical points, and when I when it says classify, that means tell me if they're local maxes or mins. So did you guys get critical points at -2 and 3? Okay, so when you do your sign line, smaller than -2, so if you put in -3, you should get a positive. But in between -2 and 3, you get a negative, and bigger than 3 gives you a positive. So, that means at -2, my graph was increasing and switched to decreasing. So what is that? Local max. And you can write it, do you guys like writing it as order pairs or function notation? Okay. Either way, it seems like we're split. You can do the f of -2 equals whatever, or you can write it as order pair. I don't care a bit. But you have to plug it into the original equation. So what does that give us?
3, -74, and -251. Question mark?
Well, you're actually like working it out.
Yeah.
Oh, I was not listening to what you said.
Okay.
I was just rattling off ordered pairs.
Okay, I was slightly confused.
No, so I said both, and I just wasn't paying attention.
So at 3, it was decreasing to increasing, so that's a local min. Again, write it however you want, function notation. If you put in 3, you get out -74, or you can write it as,
That's
you
what
don't
I
have to
was
have.
thinking.
Well, then I was
Alright.
confused on what you had said back to me, and I was just
I was, like, I didn't even look at what the points were. I
I
was
was
just
just-
like, oh, those are a lot of numbers. What?
a lot of numbers.
A lot of numbers, too many numbers. Okay, last one. So I want to classify these. So we need to find our critical points. So first derivative is 1/3 x. It might be helpful to rewrite that. That's saying
1/3 radical, no, cube root of x squared.
so. Does this ever equal 0?
Yeah, well,
If you set it equal to 0,
no, it does never equal 0,
you get 1 equals 0, which doesn't happen.
but it's not.
But we do have a critical point. Where's our critical point?
Zero.
It's at 0.
And that's because that's when the denominator is 0. Remember, critical points are where this function is 0 or undefined. Now, is the function itself undefined at 0? No, but the derivative is. So 0 is my critical point. So if I plug in bigger and smaller, so if I put in a -1, I get a positive. If I put in a 1, I get a positive. So what does that tell me?
There's no local max min.
Wait, because that's where it like converges.
It's flattening out there, but it never didn't create an excellent. All right. Any questions there?
This is just a activity test.
Concavity.
Concavity.
Okay, so I have a